Good morning and welcome to the first session actually for our class in here. It's a late start class. Today is September 7th. This is Physics 101. So we're going to be having regular meetings, and the first meeting we're going to go through basically what is expected from these meetings and the format also for the online class, and also introduce chapter 1 and chapter 15, okay, from the book. So this is what the plan for today is. I know quite a few of you are not here right now. Some of you are, and I'm glad to see that some people are present. And I will explain the process. It's very important that you guys understand it. You do not have to attend live, but you really must watch the recording if you don't attend live. So that is really how this works. Some of you messaged me that you already have at least one high school student that has a class going on right now. That's fine. After the class is over, I'm going to go and post this class on actually first step in YouTube, and then provide the link on Canvas. It's a good idea to subscribe to the YouTube channel, at least during the semester. Then after that, if you don't want to, you can drop off of the YouTube channel so that you can get the content right away. Otherwise, you'll have to wait when it's posted on Canvas. The link is posted on Canvas so that you can get your content. So this is in terms of the attendance. Again, the course is 50-50. Half of it is going to be online, namely the two sessions on the mornings of Monday and Wednesday are going to be online. And then on Mondays at 12:45, we meet on campus for the lab. So the lab, there is no choice about it. It has to be on campus, and the attendance is required for the lab. If you don't attend the lab, your grade will be basically suffer because it's 25% of the overall grade. So the lab attendance is a requirement. It has to be in person on campus in the room in the physical science building in room 214. That's the second floor all the way to the corner basically of the building. The last room when you're coming from the stairs or the elevator is going to be toward the end on your left-hand side. So that's basically where the room is. My name is Bouzidi Jamoui. My students usually call me DJ. This is actually not my first time here in Valley College. I taught before as a part-time. Now I have a full load here in Valley College. So this is basically where I come from. I have a PhD degree in physics, so I think I should have enough background to teach you the concepts that you have in this class, in addition to my experience also in teaching both in Crafton and Valley and other places too. My office is actually located in the same building, in the physical science building, but it's downstairs. You know, the physical science building has a form of a T. It's actually in the extension, the lower part of the T, okay? It's room 194, next to where the math and the chemistry people are. And right now it's not ready, so we can't meet really online, at least, I mean, in person in my office. We can still meet online if you really have a question, but actually we still can meet on in person if you really insist, because we can meet in the STEM Center. There is all kinds of rooms in there, and they are private rooms. So if you need help, please do not hesitate to ask, and I will be more than happy to accommodate. So this is in terms of the overall basically organization of things. Talking about speaking about the STEM Center, we will visit it actually on Monday when we meet in person in the lab. So we'll have to go to the STEM Center, part of our basically introduction to the class actually, because there are a lot of resources in the STEM Center that might be useful to you, whether it's related to physics, the class that we had before us, or math or other resources that are of use to you. So this is basically overall. In terms of communication with me, I'm going to talk about that right now because I'm going to introduce to you Canvas, the way the course is laid out so that you know where to go, what to find, and so on and so forth. So let me share with you the class. I'm in the Zoom session. So let me share Canvas. Do you guys see Canvas? I need at least one or two people to confirm that.
Yes.
Yes.
Very good, thank you. So this is the physics class, Physics 101, section 72. This is the late start, as I was saying. When you come to it, I'm logged in right now as a student. If you'll see in the bottom, it says leave student view, because I'm actually logged in as a student from your vantage point, how it looks to you when you first come to the class. So again, this is the landing page. This is where you start when you click on start here. So that's really what the models is, that's where all of the content is. So you really don't need to go anywhere other than that on a regular basis. However, there are some useful links in here in the bottom that might be of interest to you. Usually in the beginning, we have the syllabus, what about the course, myself. I already talked to you, told you what I am, who am I, okay? Also, about resources in general. So I'm going to start with here because it's important early on. So if I click on that, it takes me to this email address and this phone number. Just in case if you're running into difficulties, this is a useful place to go. You can call the help desk. You forget your password, you have a problem accessing the resources or something else, call them or email them. They should be able to help you with a lot of that, a lot of these resources. So that's a good starting point. And again, if you miss that or you cannot, always you can message me, you can call me, and if you call, you're going to leave a message. Since I'm not in the office right now, but I have access to that message, so I can call you back immediately or email you back or something, okay? So especially if it's an emergency. If not, you can always message me. So how do you communicate with me? The ideal place is here through the inbox. Since I'm logged in as a generic student who is not really a registered student, but just a test student, if I click on it, I will not be able to access it, but you will. The reason why is because this student does not have email system, is not really a registered student, it's just a test student, but you will have access to the inbox. So when you go there and you message me, it will tell me exactly which course you're coming from, because I have several classes. Most of them are astronomy, but I have 2 physics classes. So it's a little bit confusing to me if you send me an email and you tell me that you don't understand homework 3, or there is a problem with homework 3, or it's not showing, or I don't know, something has to do with the assignment, it's not clear. So it's a good idea to come to the inbox. The advantage of doing it there is that it tells me which class you're coming from. So I know at least where to go and help you with that, okay? Now, speaking about that, if you really cannot access Canvas and you want to message me, please tell me your class, tell me which class you're from. And if you're messaging me through the texting or leaving a message, please also be specific. The first thing you say is, hi, this is my name is so-and-so, and I am in such and such class. And then you start describing what you need, okay? It helps me basically get to the issue quickly and fix what needs to be fixing. As I was saying, I think I have like what? Overall about 6 classes or something this semester. So it really helps to do that. To know where the student is coming from so that they can get to the point where we need to be. So this is the preferred. Alternatively, you can email me or you can actually call me, okay? So all of the options are open, but this is the best way, is to come in here to the inbox. Again, you have the syllabus in here, and I know I sent you the syllabus, and I think there was a mistake in it. Hopefully you guys caught it. If not, it's corrected now. The units are 4, not 3. I think I sent 3 because usually I separate the syllabus of the lab from the lecture, but in here both of them are combined for a total of 4, not 3 plus 1. They are exactly 4. Okay, so hopefully you guys caught it. And the class is, as I was saying, it's a combination hybrid. There is an online version of it, which is really the lecture. All the learning is happening there, the testing, all of the things are happening online, except the lab activity is actually handled on campus on Mondays from 12:45 on campus. Okay, so that's why we have it. It's a combination. So the lecture online and the lab is in room 214. These are my office hours. And of course, you have all of the standard stuff for this class, including some of the useful resources, the link to the class. Of course, by the time you're here, you know you are in the right link. But this is actually intended also to be printed and sent to you guys, which you did receive it. There's some useful information. Laboratory, as I was saying, is 25%. Participation, quizzes, homework, and all of that, they amount to about 15% of the grade. The exams, they total 60% of your exam. There are some useful information for if you need help and things of this nature. This is my email address. This is actually my private cell phone. So just in case, if you really need to message me, please, as I was saying, be verbose in your message so that I understand which class you're coming from. And general policies, and this is the tentative schedule. As you can clearly see in here, we're going to start with measurements, and then we're going to jump to chapter 15, and then 16, 17. So we're going to finish waves and sound and light and refractions and all of the properties of wave properties, and then we're going to continue the mechanics. I'm going to talk a little bit about the content. Of course, we have the break for the Thanksgiving, so on and so forth, and you have the lab schedule. The reason why the lab schedule is laid out this way is because we have actually, I mean, the lecture actually is laid out this way, and we have to make these jumps, is because of the lab requirements, actually, because of the fact that we have one lab, and that lab person, actually lab technician who prepares all of the labs. So we'd like to keep them in the same sequence as much as possible, because there are other classes going on at the same time. I mean, other non-introductory classes that are going on at the same time, and they have equipment. So once the equipment is pulled out, the preference is that everybody will do that lab. So we really need to cover the materials covering that lab. But I'm hoping that you guys will not have difficulty with the content as we move along, as we will explain a lot of it, but if in case you need help, please do not hesitate. Again, I lost the home page in here. I don't think that I made the link. Did I make the link at the bottom? Yes, I did. But just in case, if I don't find the link to the home page in the content, it's already here. I can always click on it in here and find it. So that's part of the introduction in here. And the models pages that I was saying is where all of the action is happening, really. That's where you should be on a regular basis. There is an introductory video in here that is valid for any class. So I put that usually in here to get you started, but this is specific now to your class. So again, you can click in here to get started, or you can actually come in here and find the models link. Both of them are the same thing. Actually, if you look at the bottom and hover on the bottom, it says 4032. I'm looking at the bottom in here. If I move my mouse, it's going to lose it. So just watch in here. You're currently logged in into student view. So if I hover over it, it shows me the link. I'm going to click on it. If I come in here, it's actually the same link. So this one and that one are the same link. So it doesn't matter which one I click, it takes me to the course, which is really where we need to be on a regular basis. This is our place. Before I do that, let me go back home just to show you another point in here. There is the to-do in here. This is sometimes a shortcut to what you need to do, but please do not overlook the models itself. It's very important that you focus on that because it gives you help. I mean, here is just a short list of what you need to do and when it's due. You have stuff in here, welcome to Physics 101, which is due September 5th. That is basically just a message. And then you have in here class start reminder. That's the reminder that you received today. But for you, probably this already are removed because you already did them. So the minute you receive a message and you open it, it's going to take it away it's going to remove it. As I was saying, this is basically an introduction. The messages that you receive, one of them you received it today as a reminder that the class starts in about 15 minutes or 10 minutes or something. And then the syllabus quiz. This is important. So we're going to go through that, and then you have the introduction of yourself to the class. So those are the two assignments that are going to be graded. As a matter of fact, you see that these two do not have a grade. Those are just announcements. This is worth 10 points, and this is worth 25. It should be 20 points. Okay, it should be 20 points. Okay, I'm going to fix that one. Okay, so as I was saying, ignore this whole thing in here for right now and for all the time, unless you really are running out of time and you come in and let me see what to do. then you probably are going to do that, but don't do that. That's extremely not a good, healthy way of doing, of learning. So you come in here to the models, and this is where everything is happening in a sequence. It will help you basically get to your assignments properly. So again, it says in here, the introduction, course orientation, which we're doing right now. Then there are a couple of videos in here, okay, that you're going to, there are some links in here. Actually, this is information. If you click on it, it will take you to the landing page, okay? So that is basically, let me go back again. So conceptual worldview. So this is basically the overall, the landing page. Now, this is the syllabus again that we saw. So this is just an orientation part of the stuff. And now after you do the syllabus and you go through it thoroughly, you're going to come in here and take the quiz. If you don't take the quiz, you cannot really technically proceed. So you must do the quiz, and it's worth 10 points. That means you really have to review the syllabus, and this quiz is based on the syllabus, basically going through it, understanding what's required, what is the weight of the labs, what is the weight of the exams, what is the weight of participation, and so on and so forth. Do I need to have to take a prerequisite? What is the prerequisite for this class? And so on and so forth, okay? So those are the stuff that you're going to go through the quiz and understand them and answer them. So those are the questions that are related. Each question is worth 1 point. There are 10 questions in here. You cannot proceed because this has to be checked as marked, as done. So I'm going to come in here as a student. I'm going to take the quiz. I have 3 attempts. And if I submit the quiz right now, I didn't answer anything. So, but if I submit the quiz now, it tells me, of course, I got everything wrong because I didn't answer anything, okay? But I still have 2 more chances. So let me go back into home to just show you what happened. Actually, I should have gone to the models, okay? Yeah, let's go home. Let me see what happened in here. The to-do now, that quiz disappeared. Remember the quiz was in here already? No problem. There was an assignment in here that disappeared because you did it basically as a test student. I did it already. Okay, so that's the difference. So if I come to the models in here, now it's checked. If you remember earlier, it was not checked. If I reset the student, because this is a test student, we use it to test stuff. If I reset the student, technically it should show me waiting for, okay. So now I reset it, that quiz reappeared again. And if I go to the models page again, because I can do that for a test student, you, on the other hand, cannot reset yourself. Just to show you the difference between the two, that this, when you take the assignment, it's checked, then you're done when you submit it, okay? No matter what grade you do. But since you have 3 chances and Canvas will take your highest grade in here, please take as many chances, take full advantage of them. Unless you score 100% from the first time around, then at that point you're off the hook. If you score even 95% in an assignment and there are more chances in it, try it. You might score higher, okay? The worst thing that can happen is score lower, but Canvas will count the higher anyway. So that is the point that I'm trying to say. Never be satisfied with something less than perfection. That's really as a rule of thumb, because you can do it, okay? Then this is the content for this week. After we do that, this is the content for this week. Again, I'm a test student. It's showing me the objectives in here. For this week, again, we're doing chapter 1 and chapter 15. So again, we're going to go in here into the content. I have to really watch this link in here. Okay, I did 2 things in here for you guys. You can watch it in here on Canvas, right then and there, or you can click on this one and watch it externally. This video is 9.5 minutes, okay? This is an introduction. This is in addition to the content that you're supposed to read through. So you're supposed to read pages 2 through 5 from the textbook. And the textbook is the book that is listed in there by Kirkpatrick. Let me pause quickly in here, at least the video part of it, to show you the book, because it's important that you guys see the book. Okay, hold on, okay? This is the textbook. Okay, if you happen to have the book, the hard copy, that's great. If not, if it's only the electronic version that you have, that's fine. There is another resource, actually, it's mentioned in the syllabus that we can use also in the book by Hewitt. Okay, so that too also is a useful. Okay, no problem. Yeah, I'm responding to the message that one of you guys is sending to me. So since the message, oh, it's actually to everyone. Yes, Brock, you can go. Okay, that's fine, because the message, this class will be recorded. Okay. Anyway, I mean, is recorded actually, and is going to be posted. That's what I should have said. Anyway, let me go back to sharing the resources in here. So you really have to go through these assignments one by one, go through the recordings. This is actually from before. And then once you do, take this short quiz. Usually it has 1, 2, at most 4, 5, at most 4 questions, okay? In other words, when you watch these short videos, be very, very focused on them, okay? Take notes if need be, because there will be a quiz. Alternatively, you can read these pages and you should be able to answer the questions too. Not alternative, you have to read the textbook. Reading is required in here in this class, so it's not an option. Okay, but this reinforces the same point, the same ideas in there. So again, you're going to go to the next one, and that is about measurements. Actually, there are 2 or 3 videos. It's not always one video, so there are more of them. This is 6 minutes and a half. It talks about the unit conversion. This one is about, it's 20 minutes, so this one is kind of long, a little bit about the scientific notation and how we use it. And this one is actually about significant figures. Okay, this is 5 minutes. Take your time, but allocate time. It's critical you do that. Okay, allocate time for these things while you're doing that. Again, there is a quiz. Okay, and you will have also chances to retake the quiz. So it's not a something that you're going to. And in here, it's like a summary. This is not required. This is actually an optional reference if you need to use it, of how we handle large numbers, the powers of 10. How we handle the small numbers, again, the negative powers of 10, how we multiply the powers. When you multiply a power by a power, like 10 to the power 3 and 10 to the power 2, you add the powers. It's 10 to the power 3 plus 2, which is 5. This is the general rule. The division of the powers. The division of the powers is a subtraction of the exponents. So 10 to the power 5 divided by 10 to the power. Again, part of this one is that you should have had some math background, and this is the stuff that you would have covered in that math class. So in this case, it's 10 to the power 5 minus 3, which is 10 to the power 2, which is 100. And then raising a power to a power is multiplying the exponents. So 10 to the power 3 to the power 4 is 10 to the power 3 times 4, which is 10 to the power 12. And taking the root is actually raising to the power of that root. The square root, which is the second root, is just raising to the power of 1/2, 1 over that 2, or to the cubic root, which is in this case to the power of 1 over 3, and so on and so forth. Quartic root in that case would be 1 over 4, and so on and so forth. So again, this is just a short notation. This does not excuse you from reading those units, those pages, because they are very helpful, trying to help you get into those. It actually gives you more examples in the book on how to do them and things like that. Okay, so then we get into the oscillations, which is from chapter 15. It tells you exactly which pages to read, 304 through 308. And then the concept we're going to be introducing is the concept of frequency and period, and what is the period for a pendulum and what is the period for a mass spring system. And in here it gives you the oscillations in general, how the frequency is related to the period. And this is the pendulum, and this is for waves in general, okay? And then don't forget to take the quiz. This is 2.5 minutes. This one is the pendulum, but don't watch the entire video. I don't know, the entire video is like 14 or 16 minutes or something like that, but just stop at 4:40. I think it's 7.5 minutes or something. stop here. You don't really have to go because the video goes on and on about motion in general and things like that. And that's probably, I mean, as I was watching it myself, it's completely irrelevant, at least for this part. We may come back to this part, this same video later on. We'll do motion. Okay, this one is 4.5 minutes. So, I mean, not 4.5, it's almost 6 minutes. 4:51 is almost 6 minutes. So think about it, 6 minutes, 4.5, so we're talking 10 minutes, and this is about 12 minutes altogether videos that you can watch and then take the quiz. The quiz are very close to the videos actually, but not necessarily in as much details as in the book. Okay, so you have to go to the book and watch the book. Okay, then this is an assignment. Total points is 20 points, so this needs to be fixed. It's not 25 points, okay? So I'm gonna fix this one today. So it says in here 25 points, but actually it should be only 20 points, okay? There are 2 dates when you're what you're supposed to do. There is a September 14th due date, which is next week from today. So it's going to be a week from today when you're going to tell us all of that about these things about yourself, all of these items. When they're all listed, properly listed, you're going to get 10 points. That's the first part. The second part that is due by Sunday, the following after that Wednesday, is that you have to make 2 replies to your peers in full sentences and basically commenting on something they did or asking them questions, but it has to be meaningful. And for 5 points for each and every one of them. So if you count it, you have 2 times 5, that's 10, plus the 10 from the first one, that's a total of 20 points. So this is a mistake, and I'm going to fix that, okay? If you do that, that's basically your assignments for this week. So you're off the hook, okay? So let me go into a question. Okay, so let me go back into the models page. And this is basically the first week. There will be another page in here. This is not complete. That includes today's video. So there will be another place in here where you're going to have that, but that covers the first week. And the next week is going to be more and more similar. And I know it's kind of boring to see it repetitive, but it actually reinforces basically the structure to help you know where things are, so that next time you get all of the help you need for this class. So let me stop sharing in here. Any questions so far? Okay, here is the thing, okay? I really like it when students, that's really why I want you actually to be live with me in here to ask the questions, because sometimes as I'm talking, I may think that it's clear, but sometimes, especially with my accent, things are not that clear. So please do not hesitate to ask the questions, and don't let it go so that, okay, maybe next time I will ask a question, or maybe next time it becomes clearer. Usually it doesn't. Usually it becomes a little bit more confusing, and if we don't ask it right away. So please do not hesitate to ask. Okay. So let me share with you another screen in here. Okay, let me remove the keyboard out of the way and bring this thing in here. Okay, so again, this is an interpretation of this chapter 1. It's kind of long a little bit. And if you have a chance to get the other book or access to the other book, the Hewitt book actually is going to be very helpful to you to understand these things a little bit more. But as I was saying, those pages that I'm giving you, plus the videos that I'm giving you, I'm hoping that it would be enough resources so that you guys understand. Coming in here to the live session, asking the questions, and also discussing them with you, I'm hoping that clarifies everything for this topics covered in this class, okay? This is an introductory class, so we're going to be covering basically the topics from a very, very high basically perspective. We're not going to go into as much details as probably other classes. The topics that are covered in this class are, let me go into the drawing, and let me change the color of the pen and the thickness probably. And can I remove this out of the way? Yeah. Okay. So Basically, the topics that are covered are, of course, mechanics. And when I say mechanics, I mean classical mechanics. This includes motion plus forces plus work plus energy plus momentum. So these are the concepts that are going to be covered in this class, at least in terms of classical mechanics is concerned, okay? When we say motion is the position and velocity and acceleration. When we say forces, it's what causes those things, okay? And we're going to talk about a lot of forces, including the force of gravity, including the free fall, including the projectile motion and things of this nature, the incline and the motion on the incline. Then the concept of work is that the force will do work to change the position or change the kinetic energy of the system. The energy is an important concept in here that is going to emerge off of this, so we really need to understand that. And the conservation of energy is a big principle, okay? That is actually a little bit outside. I mean, it originates from classical mechanics, but covers things outside of classical mechanics too, okay? Then, of course, the concept of momentum and the concept of impulse, okay, and how those two are related. So it's very important that we cover all of these concepts. And in here, as a bridge between the two, there is a concept of inertia that we really need to understand. But this is basically the concepts that we're going to be covering in terms of classical mechanics. Also, we'll be covering waves, oscillations and waves. So we're going to start by, first of all, introducing what physics does, and then physical science in general, and the concept of measurement. Once we have those two, then we're going to actually jump into this, as I was saying, because of constraints in terms of our labs. Then we'll come back to these ideas in there. At some point, we're going to jump into electricity and magnetism. Which are important concepts in here related to one another. And of course, we're going to cover concepts like the electrical circuit. We're going to cover topics related to AC current, DC current, and basically transformers and all of the devices used in electricity. So this is a big topic, okay? It's a very wide open topic. Then we're going to cover atomic physics. And we're going to close it by, no, actually, we're not going to close it. I'm sorry. Before we get into atomic physics, we're going to cover a topic first, which is called the relativity. Because as I was saying, this is classical mechanics. We're going to cover these things in terms of classical mechanics. Classical mechanics has limitations in terms of how big objects are or how fast they're moving. Relativity comes in to fix those problems. It deals with the supermassive objects like black holes or big stars, or even our sun, for example, near its neighborhood, and or speeds that are close from the speed of light. Then we're going to cover that. So that's the difference. In other words, classical mechanics is useful on an everyday basis, okay? Daily activities, it's very good. But then when you go on extreme fast moving objects or extreme large objects, then that fails. So we need to know how to fix that. Then we're going to cover atomic physics. And finally, we're going to close it by talking about nuclear physics. So the topics are big and wide, and each and every one of them can take a whole semester, okay, just if we go in detail. So we're going to cover them in general and trying to go from one idea to the next and so on and so forth. At some point, we're going to talk about thermodynamics and heat. So heat actually is going to be immediately after the momentum and all of that. So we're going to talk about heat and temperature. So these are the topics that, as you can see, it's a big, ambitious project in here that we're undertaking, and hopefully you guys will enjoy it along the way with me, okay? Okay, the first thing first, which is from chapter 1, is basically what is studied in physics, what do we study in physics, and how physics evolved, and so on and so forth. Okay, and the physics, of course, study the motion. That's one of the things that we described earlier, and attempts to make predictions. Okay, based on what you know today, what will happen tomorrow. That's basically, in a nutshell, what a physicist does. If a car is moving at 50 miles per hour and it's on highway 215, for example, going north, and right now just past the intersection with highway 10, how long will it take to meet highway 15, for example? If you know the distance, you know the speed, you can figure out the time. So you made a prediction. Okay. And in this case, you have to use the laws of physics to make that prediction, to make the prediction. Obviously, that prediction needs to be tested. In other words, if you say right now, for example, what is it, 9:36, and you make the calculation and you say the car will arrive in the intersection, what is that called? Cajon Pass is going to get there at 10:02. And not only 10:02, 10 at the hour of 10, the minute of 2, and the seconds in 13 seconds, okay? You make a prediction, accurate prediction. Somebody has to go and test that. Somebody actually has to take a measurement. Like the driver, for example, the minute he or she reaches that point, says, okay, I just reached the point. Then you look at the clock and you say, okay, was my prediction correct or not? So this is basically, in a nutshell, some of the things that we do in physics, okay? Obviously, I'm going to rely on laws. And this is really the foundation of things. When I was talking about the motion and the forces and everything, they're governed by laws. So what is a law in science? A scientific law has to basically withstand time. Every time you test it, every time you run a test on that law, it never fails. For example, if I take an object, I have an object like this one in here, okay, and if I let, by the way, it's here, okay, and if I let go of it, it's going to fall. This is the law of gravity. If I let it go, it's going to drop all the time. And I actually can measure the distance and the time it takes to fall, and I can make it into a law. The minute this fails, in other words, if I let go of it and it stays suspended for a little while, or it goes up on its own, or for some reason it speeds up more than it should, or slows down and goes slowly, then that law is no longer a law. I have to revise it. I have to come up with something better. So it has to withstand time, and it has to be testable. So you cannot just come up with any law and then say this is a law. Which brings me to the scientific method that is represented in this diagram that you guys see in here. Okay, usually it has this representation. So if you Google scientific method, most likely you're going to come up with a form that looks exactly like this one, if it's not very close from it. So the scientific method, if you read in the book, it's really coming from, it evolved over time. Aristotle and the philosophers, they were thinking, most of them, they were philosophy, by the way, and there is a big distinction between philosophy and physics. Physics is best based on testability, and philosophy is basically deduction, reasoning. But then came around the 1500s, Mr. Alhazen came up with the idea of the hypothesis, and he laid the foundation for it. Later on, it was further refined by, among other people, was Newton and other scientists, basically, on how to formulate the scientific method. And it's represented in more or less this diagram. So you make an observation, or you do an experiment, and then based on that experiment, you gather the conditions of that experiment, see what happened to it, what are the conditions for it. Again, for the law of gravity, for example, the free fall, the condition is I don't have air blowing. If the air is blowing, I will notice that this will drift a little with the air. So if I insulate it and I put it in a vacuum, then that law, the one I was describing earlier, should work all the time, okay? So these are some of the conditions. So make sure that you're in vacuum and you're testing. So now you make a hypothesis. Okay. And the hypothesis has to have a structure in it. One of the structures for it is that you can test it, and that testing can, there is a room for it so that you can test it and how it fails. Okay. Let me give you an example, okay, from astronomy. I teach a lot of classes of astronomy. So I'm going to give you an example. Aristarchus, who was about 300 before the current era, made an observation based on the solar, I mean, the lunar eclipse, based when the moon is a quarter moon. He made a calculation and he calculated that the sun must be bigger than the Earth. He came up with an error. He thought it's about 7 times bigger. Based on his measurements of the angle, which was a little bit off, he came up with an 87 degrees. Today we know it's actually much more than that, 89.51 degrees. 89 degrees and 51 arc minutes. So it's almost 90 degrees. But the point being in here is he measured the distance to the moon. He measured the distance, basically, compared to the size of the Earth. Everything was relative to the size of the Earth at that time. He didn't know how big the Earth was. But the point being in here, he came up with an estimate for how big the sun is compared to the Earth. First of all, the sun is bigger than the Earth. And he came up with an estimate about 7 times. Forget about the estimate of how big it is. The mere fact that the sun, in his consideration, was bigger than the Earth made it so that he said, wait a minute. The sun cannot orbit the Earth because it's bigger, according to him. The Earth must orbit the sun. So he made a hypothesis in here based on these observations. Can you see how this thing works? There was a flaw in his argument, and rightfully so. If it is true that the Earth orbits the sun, then the stars, they should shift in the night when we see them. If the Earth is on this side of the sun, and I'm looking for a star, it doesn't matter, pick a star, Ceres, for example, that star, when we are on the other side, should shift, just like, for example, when you change positions and you look at a mountain or you look at something, it should shift. This is called the parallax. So his hypothesis has in it how you test it. And the testability in this case is called the parallax. Because we cannot see that shift, people argued that, wait a minute, that is not a good hypothesis. They rejected his idea that the Earth orbits the sun. The sun, they said, must orbit the Earth, just like everybody else. Obviously, the flaw in here was in the fact that the distance to the sun between the Earth to the sun and the distance from the Earth to the stars, there is a huge comparison. There is a shift, but it's unnoticeable to our naked eyes. So the point being in here is the hypothesis has to be testable. Once you test the hypothesis and you come up with an experiment to test it, you take the data, and that data, you analyze it, and then you come up with the basically refine your hypothesis further and go back through the process. It looks like it's cyclic and it looks like more linear. In reality, the process is not that easy. The process usually involves, sometimes you come into a hypothesis and then you go backward and refine the experiment and do the observation. Sometimes the process is not that linear. But just to give you an idea how the scientific method is. Making a hypothesis, and the book gives you all kinds of examples in there that are accidental, basically, connections or incidental connections that are not basically related to one another. In other words, if I'm going to test how this quantity depends on how the other quantity, then I really have to have that connection between them and test it further down the road. It gives you the example of the Boyle's law. It turns out to be not a law at all, about the motion of planets and so on and so forth. Okay, so which brings me to another point in here. If I'm going to test something alone, I really have to come up with a measurement system. Okay, how do we measure things? Okay, it's very important, because if I'm going to, first of all, what is measurement? Because a very important step in the experimentation is the measurement. So here is the process. I come up with a standard and say, this is a standard. I'm going to call this one the unit of whatever I'm measuring, okay? Like, for example, the distance, I'm going to call the angstrom the standard. Small distance. If I'm looking at the atoms, yes, it's good, but not on a daily experience. But that's my thing. If I'm looking at the distance between the stars, I'm probably going to use the light year. That's a good number. The distance between our sun and the nearest star is about 4 light years. Some people, they use a palm. I remember that in the old days, they have the palm. How many palms there? This is, so that was part of the pace. Also, Fermi, which is even smaller than the angstrom. The angstrom is the size of an atom. This one is actually the size of a proton, Fermi. So depending on what you're doing, but the standard unit now that is accepted is the meter. Okay, so this is a standard. Is it right or is it wrong? The question is meaningless. It's just a standard. We agreed on it, saying that this much, probably slightly more, trying to fit it into the screen, this much is a meter. Okay. Instead of calling it Napoleon's arm as being the unit of length, then that's not a useful thing, okay, because Napoleon is dead a long time ago. But that's basically the standard for the distance. Now, if I'm interested to measure how big this desk is, I'm going to take the standard and compare it to my desk. And so many and ask how many times do I have of my standard compared to the desk. Then I come up with a number. So this is how you conduct an experiment. So measurements really involves comparison to a standard. Okay. You compare something to a standard. The same thing. So now the units for length are the meter. This is the standard that is accepted in the Système International, which is the international system of measurements. I know here in the United States, we have all kinds of units. We have the yard, which is just slightly less than a meter. We also have the feet, we have the foot, I should say. We have the inches, we have the mile, and the conversion between them is a nightmare. Just to give you an idea how much a mile is in terms of inches, the mile is 5,280 feet. If you want to know how many inches that is, because you have 12 inches per foot, then in this case, you're going to multiply by 12 and divide by 1 foot. This is how you make conversions, by the way. You always divide by the unit you want to get rid of. In this case, the foot and the foot cancel, and the answer will be in inches. Always the unit you want to go to needs to be in the numerator, and the unit you want to get rid of is in the denominator. So if 12 inches is 1 foot, this is an equality. I could have written it as 1 foot over 12 inches or 12 inches over 1 foot. Which one I should use depends on where I'm going from. Since I'm going from feet to inches, I should use the feet in the denominator to get rid of it, so that the foot and the foot cancel, and then I'm left with inches. But the answer is a ridiculous number, 63,360 inches. So that is how the conversion, and again, it goes you in detail to show you how you do that. So the unit for length in the Système International, which stands for SI, and it talks about it in the book, hopefully you guys will go through it. This is the meter. So this is what people agreed on being the unit of length. Also, I'm going to write somewhere in here, probably. Let me add a new page in here, just to, and let me move this page a little bit here. And let's change the color also. Or leave it, okay, but I need to change the color of the pen. Okay, so we have the unit of length is a meter. So this is for length. The symbol for the meter is M. We have the length, the unit for mass is in kilogram. And the symbol for it is K. Actually, it's kg, but for my notations in here, I'm going to put the K because I'm leading to a representation. This is in the SI. The SI is the system. Why is it doing that? International, which is the standard, basically. Okay, that we're using in here. Okay, so the kilogram is for the mass, and also for the time is second. This is for the time. So the symbol for it is S. And the last one for the System International, which is going to cover in part of electricity, is how much current we have. So the current is actually in ampere or A. That's what the System International sometimes is referred to as MKSA. Okay, so this is the system, international system, if you like. International disunity or unity, I don't know. Okay, in other words, the international system of units. Okay, this is the one that we're going to be focusing more most of the times. If you're asked to do a conversion like I did in here, like this one, you're going to be given the units to use. Okay, so you should be able to know what units to use and so on and so forth. Okay, because how many feet in a yard? So you need to know that. Okay, and if we're going to go from an inch to a centimeter, how many of those things? Okay. Again, this problem in here can be solved by the system, the SI system that I was saying, because it really uses the base of 10 as multiplication. So in other words, for example, if I want to know how many grams in a kilogram, well, it's easy. A kilo is 1,000 grams. So that's the answer. The answer is built into the word itself. How many meters in a millimeter? So a millimeter is 1,000th of a meter. So in other words, the answer is built in there. A centimeter is 100th of a meter. So these words in here are built, they have the answer in them. So you don't really need to Google or look or find how many inches in a foot? Oh, it's 12. Then I'll have to use 12. No, this one it's always in basis of 10. How many meters are a tera meter? Well, it's 10 to the power 12 trillion. Okay. Gigameter or gigakilogram or a gigahertz. Your phone uses gigahertz. How many hertz in a gigahertz? Well, giga itself is 10 to the power 9 or a billion hertz. So the answer to that, it's built into the word itself. That's why the metric system actually is far more useful, because you can find everything inside of it. Okay, so if somebody tells you, okay, you have a distance, these are already the centi and the milli. For example, the size of a microbe is 3 micrometers. So you ask a question, how big that is? Well, 3 micro is here. It's 10 to the power 6 or a millionth of a meter. So 3 millionth of a meter. So the answers are built into them, all of them. And then you have the nano, the pico, and the femto. Okay, I have not seen anything smaller, at least that we know of, smaller than the femto. I mean, probably the Planck lengths, but all the things, but we're not going to be dealing with these things. I already shared with you that resource on Canvas on how to do the powers. and how to handle the powers, but this is just in a nutshell how you do that. Again, the book goes a little bit more details. That intro that I showed you, which is already on Canvas, should help you with that. The bottom line is, if I have a power, like I was doing in here, a million, 10 to the power 9, for example, and so on and so forth. If I have a power, it doesn't matter which, A, and if I want to multiply it by another power, 10 to the power B, as a general rule, just add these two numbers, that's all, and put them in the base, okay? Of 10 in this case, okay? So that's the answer to it. And in here, I can read this one as 10 to the power 1, and this is 10 to the power 1, and this is 10 to the power 1. So the answer really is 10 to the power 1 plus 1 plus 1, which is 10 to the power 3, okay? Because 1 plus 1 plus 1 is 3. So 10 to the power 3 times, which is 1,000, because if I take 10 times 10 times 10, that's 1,000. So that's one way of looking at it. The negative numbers are the inverse of that. They're basically the fractions. So if you see a negative number, all you have to do is just invert and put the power positive in this case. So again, 10 to the negative 2 is 1 over 10 to the power 10, which is 1 over 10 times 1 over 10. And again, 1 over 10, you can put a 1 in here if you like, 1 in here and here. So 1 plus 1 is 2. It's exactly how it's supposed to be, okay? And 10 times 10 is 100. So this is 1 over 100, which is 0.01. So again, this is how you represent the decimal numbers, which is, again, another way of looking at this is 10 to the power A divided by 10 to the power B is nothing but 10 to the power A minus B. This is part of the stuff that you have seen already in the other classes, in the algebra class. 10 to the power A to the power B, this is a little bit more involved because you're raising a power A to the power B in the base of 10. So it's going to be 10 to the power of A times B, okay? So that is basically how the answer to this one is. And the notes give you something very useful. Let me share with you another resource before I go down here, which is important. The scientific representation. In the scientific representation, a number 357 needs to be written in such a way that there is a number between 1 and 10, more than 1, more or equal than 1, more or equal, but less than 10. This number in here times a power of 10. So that's how the scientific representation here is 357 more or equal to 1. Of course, it's more than 1. So this part, we're done with it. Is 357 less than 10? Obviously, it's not. It's more than 10. So the 357 is not in scientific representation. So I need to bring it to a scientific representation by making it look like a number between 1, including 1, and 10, excluding 10. In other words, it could be 1, it could be 2, it could be 3, it could be 4, it could be 5, and it could be all the way to 9, but it cannot be 10. Since this number is clearly more than 10, then I have to divide it by 10 and see what happened. If I divide it by 10, 357, if I divide it by 10, well, the answer is just move the decimal point 1 step, and the answer is 35.7. And ask myself, is 35.7 more than 10? Or I should really ask the question, is it less than 10? The answer is no. Since it's less than 10 is no, then I have to divide it further by 10. So 35.7 divided by 35.7 divided by another 10 will give me, move the decimal points another step in there, 3.57. Now the answer is 3.57. I ask myself, is 3.57 less than 10? The answer is yes. So I found a number that is greater than or equal to 1, but less than 10, which is 3.57. So now I have that number, but I need to the power of 10 in here. The power of 10 is coming from this 10 and this 10. This is 10 to the power 1, and this is 10 to the power 1. So if this is 10 to the power 1 plus 1, in other words, 10 times 10 is 10 to the power 2. So I have to have it like this. So 357 can be written in scientific notations as 3.57 times 10 to the power 2. In other words, 3.57 times 10 times 100. So that's perfect. This number now fits the description. It's equal to or more than 1. It's not really equal to, it's more than 1. But the requirement is that it has to be at least equal to 1 or more than 1. But less than 10. It cannot be 10. And this number is definitely less than 10, 3.57 times 10 to the power something. Let me give you another example so that we have this idea clear. 0.00231. Okay, I ask a question. Is this in scientific notation? For that, we have to ask a question. Is this number more than or equal to 1 and less than 10? The answer is no. This number is less than 1. So this number is not in scientific representation. I really have to fix it so that this number is at least equal to 1, but cannot be greater than 10. Cannot be actually equal to 10. It has to be less than 10. Okay? So this number is smaller than 1. So what I do in this case is multiply it by 10. Here, I divided by 10 because the number was more than 10. Here, in order to bring it up to par, I have to multiply it by 10 to bring it up there. So if I do that, then the decimal point will shift from here now to the opposite direction. So the answer is going to be 0. So this 0 doesn't mean anything. I can write it as many zeros as you want. So I am going to shift the decimal point in here. And the answer is 0.231. Since this 0 is extra, we just drop it. Okay, 0, 0 is the same as 0. So it's 0.23. And then I ask myself, is this number greater than or equal to 1 and less than 10? The answer is no. It's still less than 1. So I have to bring it up. So I have to multiply the answer by another 10. Here is the answer that we found, 0.0231 times another 10. And I ask myself, what is the answer first? Well, I have to shift the decimal point in here one step in here. So again, I have that extra 0 that is from before, but I have, when I shift the decimal point one step, it's going to be the 0 here and 2, 3, 1. Of course, this 0 is extra. 0, 0 is the same as 0, so it doesn't matter if I write it in there or not. And then ask myself, is this number now 0.31231? Is this number now bigger than or equal to 1 and in the same time less than 10? The answer is no, it's still less than 1. So I have to multiply it one more time. So the number that we ended up with last time is 0.231. So if I multiply it by 10, I move the decimal point in here. So it's going to be 0.231. The 0 is insignificant and the 0.2 is the same as 0. Put it on Excel or on a calculator, it drops it completely. So the answer is 231. I ask myself, is 2.31, is this number bigger than or equal to 1? And in the same time, less than 10? The answer is yes. Because this 2 is more than 1 actually. And the answer is yes. So in this case, I have found that part and the decimal representation, which is here. So it's 2.31 times. Then I have to find the powers. Remember before when I was dividing by 10 to bring it to the standard, I had to 10 to the power and then I added these powers. Now I have to subtract them actually. I have to write 10 to the power and then I have to be careful. How many 10s do I have involved? The first one was here, the second was here, and the third one was here. So there were 3 of them. But because I am shifting the decimal point in the other direction, so I'm going to put a negative number. This is the same number as you saw before, 0.00231 in scientific representation. So it fits the bill now. This is the same number that has a digit in here that is more than or equal to 1, but less than 10. 2.31 is more than or equal to 1. Actually, it's more than 1. And it's less than 10. You could have 9.999 in here and it's good. Or you could have 1.0 in here and it's good. But you cannot have 0 point something. That is not acceptable. Or you cannot have 10 point something. That is not acceptable. This number in the scientific representation has to be between 1, including 1, and 10, excluding 10. So as long as it's there, this is the scientific representation. Time is a power of 10. It doesn't matter what the power of 10. In this case, it's a negative power, and the first case, it's a positive power, okay? So this is the distinction for how to write numbers in scientific representation. So when we were talking about it in here, this is what we mean by it. I'm not going to hold you accountable for this because this is part of your math class, but a lot of the problems that you'll be dealing with, they will have numbers in scientific representations. So you really have to be to understand how these things work so that you will be able to work out these things, okay? Okay, which brings me to the second part of this week's basically discussion, and it has to do with the pendulum, it has to do with the waves, and it has to do with the oscillations. So we're starting actually with the oscillations. So it's an oscillation is like a motion of a pendulum and a mass suspended from, I mean, not mass, pendulum, a spring and mass suspended on the spring. So if you take spring and you put a mass on it and you wait for it to reach its equilibrium position, it's going to stay there. It's not going to move. But if you disturb it out of its equilibrium position, it's going to go on and off, on and off, on and off. So we call this motion an oscillation, okay? So oscillations are periodic motions, motions that repeat. That's what it means. Constant. And the time of repetition, since I have this introduction in here included, so let's continue the other one in there. This is like the blackboard that we use on campus. Actually, we use whiteboards, I'm sorry. Except that I have it in here, so that's why my notes are on this blackboard in this case. Anyway, so what we have in this case is we have a periodic motion. So if I take the mass spring system that I was describing in there, so I have a spring in here, and I attach to it a mass, and I wait for it to equilibrium. So in this case, it's in equilibrium position. Nothing will happen as long as it's sitting in there. Initially, because of the weight of the mass, it's going to displace it. The spring is going to stretch a little. The spring has a spring constant called K, okay? In order to stretch it a lot, you really need to apply big force. That's what that is. So the force you need to apply depends on how much you stretch it. Okay, so the stretching, how many meters you're going to move it out of its place, okay? That's what that means. So this is the displacement of the spring. Displacement. This is the properties of a spring. I mean, take a stiff spring, the one used for cars, for example, or trains, and it requires a lot of force to even move it an inch or less than that. For weak springs, for example, the one that you get from Home Depot, the small ones, you just basically barely with anything and they're going to stretch. So this is a property of the spring. This is called the spring constant. When you buy spring, it comes with it. They tell you how much its spring constant is, depending on its construction. And the mass has a mass m, so the suspended mass has a given mass m, okay? Now, if you disturb it out of its equilibrium, the mass spring system will oscillate. So now it's disturbed, it's no longer, so it's stretched, in other words. And this is the old equilibrium position. The object will go up and down. The spring will stretch all the way, and you let go of it, It's going to compress actually back to its equilibrium position, but it's not going to stop there. It's going to continue its compression, and it's going to go all the way back to the opposite direction. So in other words, at some point, it's going to look like this. And still, this is its equilibrium position. So it's going to go up and down, and this is a phenomenon that you should have seen and you should be experienced with. And then it's going to go back to an equilibrium position, and at some point it's going to continue stretching until it reaches the original position that you stretch from, and this motion repeats. That's why we call it periodic motion, because it repeats. And the period of oscillations, because this is an oscillation going up and down with respect to the equilibrium. So the period is T. T is the period. So what is a period? It's the time it takes to go from this position back to the same position that you start from. It doesn't matter which position. Alternatively, I could take the Y position of the spring and represent it as a wave, actually, as an oscillation in this case. So if I keep tap of the time, the spring, when I stretch it, it was fully stretched in here. Then when I let go of it, it's going to completely go back to the equilibrium position. And then it's going to go completely in the opposite direction, which is here represented in this case. And then it's going to go back to the equilibrium position, which is represented in here. And then it's going to go back to where you started from, and the process will repeat. Okay. The time it takes to go from one state to the same state as before, this is the period, T. And it's measured in seconds. Okay. We're going to introduce just this concept, and we're going to stop right now because I know probably we covered a lot of stuff today. So, and I hope that you guys will go and do the reading. We're going to introduce the concept of frequency. And the frequency is how many oscillations do we do in 1 second? That's really the question. We do one oscillation in T time. In 1 second, which is the unit of time, we do F oscillations. This is by definition the frequency. Well, it's clear from here 1 times 1 is equal to T times F, so F is times T is equal to 1, which means that the frequency is just the inverse of the period. So this is basically in a nutshell how we have the two. So the time T, which is period, is measured in seconds. And the frequency F is measured in 1/seconds, frequency in 1/seconds, or Hertz. It's the same thing. In honor of Mr. Hertz, who did a lot of work in this, in the electromagnetic waves and propagation of lights and so on and so forth. Okay. Okay. So this is the introduction to the oscillations. When we meet next time, we're going to talk about the frequency of the mass spring system. We're going to talk about the pendulum. We're going to talk about the pendulum. We're going to introduce the waves, and the distinction between a wave and an oscillation is that the oscillation is local. In the case of the mass spring system, the motion is up and down, but it's in the same location. In the case of the pendulum, it's going to oscillate back and forth, but it's in the same location, so it's localized. Versus the wave that propagates throughout the medium. For example, the sound that I am speaking right now, it's actually a wave. And that wave propagates through the medium in this case, which is the air in this room where I am at. And this wave will travel all the way to the speakers, which are attached in here. And those speakers can be taken by the by the electronics of that speaker and be converted to an electrical signal that goes through the wire and then comes to your device as an electrical signal. Your electrical signal then will take it to the speaker, and the speaker basically will act as a broadcaster of that same wave that you're hearing from me right now. So again, it's going to propagate as a wave inside the room where you are, and it's going to be picked up by your receivers in this case, which are your ears, and that's a wave, that's sound wave. So waves in this case are a little bit different than the oscillations in the sense that they are not localized, they propagate, they move through the medium. Okay. Any questions? I know some of you are relying on this recording, a lot of you are, so hopefully you guys will watch the recording later. For those who are not live, okay, and will join me next time, which is going to be on Monday, the same time. You're going to be receiving a notification. Actually, it's the same link that we have right now, so it's not going to change throughout the semester. And we're going to talk about basically finish this topic basically, and then finish this units, and we'll kind of continue with the sound and so on and so forth. Sounds good, everybody?
Yeah.
Good. Okay, very good. So I'm going to stop the recording unless you guys have a question, and I will see you Monday. Or for those who are going to be watching the recording, please remember that the lab on Monday at 12:45 is a live person. It's not an online. So I don't know how far you're going to drive, but please make sure you get into the lab session in time. You have more than 2 hours to get there. So no matter how far you are, you should be able to make it, okay? Because we are in the San Bernardino area, we should be able to get into campus, okay? Okay, so I'll see you guys next week. Thank you.